Good morning, children. We are discussing the next chapter, electrochemistry. In this chapter, the chapter starts with the study of the basic definition of electrochemistry, or what is electrochemistry. As we know that electrochemistry is the study of the production of electricity from the energy released during a spontaneous chemical reaction. So whenever a spontaneous or a continuous chemical reaction is been taking place, amount of energy released, that is actually called as electrochemistry, or the source of energy from some chemical reactions. Now the first thing we should discuss about Ohm's law. It states that the potential difference V across the conductor is directly proportional to the current flowing through it, or I can say V is directly proportional to I, or V equals to I into R, where R is the resistance, where R is the constant, and this constant is called resistance of the conductor. Ohm's law is obeyed by both the metallic as well as the electrolytic conductors. Now we have the next point, that is the resistance. What is resistance? The resistance is represented by the symbol R. It is the property of a substance by which it obstructs the flow of electric current through it. The electric resistance R of any object is directly proportional to its length L and inversely proportional to the area of cross section A, or we can say that R is directly proportional to L by A, or R equals to rho L by A, where rho is constant or proportionality, which is called as the specific resistance or the resistivity, or we can write rho equals to R into A by L. If L equals to 1, A equals to 1 centimeter square, then R equals to rho. Thus, the resistivity may be defined as resistance offered by a conductor of 1 centimeter length with area of cross section equal to 1 centimeter square. Or I can say that the units of rho equals to R A by L, or it equals to ohm centimeter square by centimeter, or it ultimately comes to ohm centimeter. Its SI unit is ohm meter, and it is represented by this symbol omega. Right? After that we have conductance. Conductance is represented by the symbol G. It is the reciprocal of the resistance and may be defined as the ease with which the electric current flows through a conductor, or I can say G equals to 1 by R. Whatever the value of resistance, its reciprocal is conductance. And the SI unit is Simon. It is represented by the symbol S. 1 Simon equals to 1 ohm, 1 ohm to the power minus 1, or it is mho. Now conductivity is represented by symbol kappa. It is the reciprocal of resistivity. So as we know, the reciprocal of resistivity is conductivity, and the reciprocal of resistance is conductance, and it is given by this formula: kappa equals to 1 by rho equals to 1 by R equals to L by A, or equals G L by A. In this way we discuss about conductivity. Yes, children, after that we are going to discuss about factors affecting metallic conductivity. What are the factors that affect metallic conductivity or the metallic conductance? See, the electrical conductance through the metal is called as metallic or electronic conductance, and is due to the movement of electron. It depends on various factors. What are the factors? The nature and structure of metal, number of valence electrons per atom, and the temperature. These are the three basic factors on which the metallic conductance depends. After that, factors affecting electrolytic conductance. Now, what is an electrolyte? Electrolyte is a substance that dissociates in solution to produce ion. Suppose I say that all strong acids, all strong bases and salts, they behave as excellent electrolyte. Why do they behave as excellent electrolyte? Because they on ionization produce large amount of ion. See, here they are given example: HCl, NaOH, KCl, all these are strong electrolytes. On the other hand, see, acetic acid, ammonium hydroxide is examples of weak electrolyte. Now see, the conductance of electricity by ions present in the solution is called as electrolytic conductance, and it depends on the following factors. What are the factors? Nature of electrolyte or inter-ionic interaction. Now, what we know, lesser the solute-solute interactions, greater will be the freedom of movement of ions, and higher will be the conductance. Next is solvation of ions. Larger the magnitude of solute-solvent interaction, greater is the solvation and lower will be the electrical conductance. Third is the nature of the solvent and the viscosity. Larger the solvent interaction, larger will be the viscosity and more will be the increase. Next factor is temperature. That is, as the temperature of the electrolytic solution rises, the solute-solute interactions will obviously, what will happen? They will increase and the solvent-solvent interaction will decrease, which results in the increase in the electrolytic conductance. So this part should be very much clear to you, that larger the electrolytic conductance, larger is the temperature, more is the electrolytic conductance. After that, we will discuss about the basic differences between metallic conductance and that of electrolytic conductance. See, in a metallic conductance, it is the movement of electron responsible for conduction. We have seen that metallic wire by which current passes, it is because of the movement of electron responsible for it. Now, electrolytic conductance, it depends on the movement of ions is responsible for the conductance. Now, see, metallic conductance does not involve transfer of matter, but electrolytic conductance, matter moves in the form of ions. It decreases with the increase in temperature as kernels start vibrating and produce hindrance in the flow of electrons. Increase with the increase in temperature due to the decrease in ionic interactions. After that, we will study the measurement of conductance. As we know, here we have Whitson bridge. By this Whitson bridge, we will calculate the measurement of conduction. As we know that conductance kappa is equal to 1 by R into L by A. The value of kappa would be known if we measure L, A and R. The values of resistance of solution R between two parallel electrodes is determined by using the Whitson bridge method. Whitson bridge method. In this method we have, see, we have resistance 1, resistance 2, resistance 3 and resistance 4, and resistance 2 is the conductivity cell, and the value of R2 we can calculate from this equation. R1 by R2 equals to R3 by R4, or we can write R2 equals to R1 into R4 by R3. So by this method we actually find out the measurement of the conductance of the electron. So after that we are going to discuss about molar conductivity. Now, what is the meaning of molar conductivity? Molar conductivity is defined as the conductivity power of all the ions by dissolving 1 gram mole. As it is molar, we are dissolving 1 mole of electrolyte placed between two large electrodes 1 centimeter apart. It is mathematically given by the equation, that is molar conductivity equals to kappa into V equals to kappa by 1000 by C, where V is the volume of solution in centimeter cube containing 1 gram mole of electrolyte, or the units pi m equals to kappa into 1000 by C, or equal to S per centimeter by mole per centimeter cube, or that comes to ohm to the power negative 1 centimeter square by mole negative 1, or it ultimately comes to S centimeter square by mole inverse. The variation of conductivity and molar conductivity with concentration. See, conductivity decreases with the decrease in the concentration. This is because the number of volume that carry the current in the solution decreases on dilution. Thus, molar conductivity pi m equals to kappa into V, and in this way we get this type of graph. In this we have plotted this molar conductivity by this, and here we get that as the weak electrolyte changes to the strong, we get this type of values. Okay.